here we have the fundamental theorem of calculus, which says that if f is continuous on the closed interval from a to b, and capital F is an antiderivative of little f, then we have that the integral from a to b of f of x with respect to x is the antiderivative evaluated at b, subtracting the antiderivative evaluated at a. Before we go ahead with the proof of this, we need to prove something first. So here we have a statement. Let f be a continuous real-valued function on the closed interval a to b. If we define capital F of x to be the integral from a to x of some function f of t dt, so some dummy variable, then we have that the function capital F is differentiable on the open interval from a to b, and the derivative of capital F of x is just little f of x. So we're going to use this statement here for our assumption for the next statement. So let's go ahead with the proof of this first statement. So we want to show that f is differentiable on a to b. So the way we're going to do that is, let's find the derivative of capital F of x. So capital F of x. So this is just from first principles. You take the limit as h approaches 0 of f of x plus h minus f of x all over h. And we can split this up, so I'll just work on this bit separately. So f of x plus h, well, just given the way we've defined f of x here, if we substitute x plus h instead, we get that it equals the integral from a to x plus h, f of t dt. And I'll just rewrite how we've defined f of x, because that's what we have in our equation there. So we have that f of, so if we look at this numerator here, I'll just write it out explicitly, x plus h minus f of x. Well, that will just be integral from a to x plus h f of t dt minus the integral from a to x f of t dt. And you'll probably notice that if you have, so you have from a to h, integral from a to h, and you're subtracting, so obviously x plus h is larger than x. So this is a larger, you could say, width than this one here. So if you're subtracting whatever the integral from a to x is, you're just left with the integral from x to x plus h f of t dt. So it's hard to argue with that one. Next, we will look back at our original equation there. So we can rewrite f dash of x. So limit as h approaches 0. So this whole thing, I could just write that as the numerator times 1 over h. So 1 over h. So it just makes this setup a bit neater. 1 over h x to x plus h f of t dt. Now what we'll do, we'll have to employ the mean valued theorem for integrals. So there's different versions of the mean value theorem, one specifically for integrals. I could go ahead with writing the statement out in full, but I'll just, I think the best way to explain it is to, or in this context, is to illustrate it. Even though it is quite difficult to illustrate, say if we have a Cartesian plane here, you have, let's say, some function that goes like that. You have x, and you have x plus h here. Well, before I do that, I think I'll just probably mention the statement. So the mean value theorem, for integrals. So this, we can use this only if our function is a continuous function. So it implies that there exists some value c inside the interval x to x plus h, such that so the integral from x to x plus h f of t dt equals f of c times h. So what this means is, if we're considering this left-hand side here, so we have some function as we've drawn here, and we want to evaluate the integral from x to x plus h. The mean value theorem for integrals says that that is just equivalent to some f of c for some c times by h. So say if we have c here, it could be anywhere between x and x plus h. So if we look at the right hand side, actually, note that this width, or neither, from here to here is just h. So f of c is over there. If we multiply f of c with h, we just get this rectangle. And what the theorem suggests is that for some value c, we have that this rectangular area is equivalent to the area from x to x plus h. So this area, in some sense like the exact area from x to x plus h, is equivalent to the rectangular area that is the length of h multiplied by the width of f of c, or vice versa. So hopefully I've made that sufficiently clear. This is where I've drawn the c here is just, it could be anywhere in between x and x plus h. The theorem says that there must be some c between this interval such that those two areas are equivalent. Okay, so we have this statement here. What we can do now from here is this section here can be written as f of c times h. And this just simplifies to f of c. So capital F dash x, we said from here, it's the limit as h approaches 0 of just f of c. And what happens if, so h, remember, is just this width. And if you have h approaching 0, that means this width is approaching 0. And as it approaches 0, this width gets smaller and smaller until you're just at the point x. So the limit as h approaches 0 of f of c is just f of x. So what just happened? If h approaches 0, c approaches x. So we have that, well, we have what we want, which is the derivative of capital F of x is just little f of x. So that's just the first part, and we need this part because we need this result to prove the theorem, the fundamental theorem of calculus. So I've got a bit of space here, I'll just move everything up. So recall that the theorem states that if f is continuous on the closed interval from a to b, and we have f an antiderivative of f, so this result, then the integral from a to b of f of x is capital F of b minus capital F of a. So let's go ahead with the proof. So we've already shown, so we have shown that f dash of x is f of x on a to b. So what we're going to do is we're going to consider our interval from a to b. Let's split it up. Let's partition it into little bits. So we'll define a as just x naught, and we're going to split it up into little into points, x naught to x1. And you continue this up to xn, which is the final point in the interval, which is just b. And our width, change in xi, is just the difference from one point to the previous point. So now what we're going to do is employ the mean value theorem again, this time not not the integral version, but just the classic version. So I'll just write out what the theorem says in general. So let f defined from a to b to r be a continuous function on that interval a to b, and differentiable on the equivalent open interval. Then there exists some point c in the interval from a to b such that the derivative evaluated at c is just f of b, so the gradient, so f of b minus f of a on b minus a. Okay, so I should sketch a little cartoon to illustrate this as well. You have some point, say, with the coordinate a and f of a, another point where b is greater than a, say b, f of b. You have the line joining those 2 points, and you have some function going like this or whatever. Actually, let's go like that. Then what this mean value theorem is saying is that there is some point c. In this particular case, the c would lie pretty much right here, c and f of c. The reason it's here is if we consider the tangent line to the curve at this point. It's almost parallel, but these 2 lines, they will be parallel. For some c, when the tangent line is drawn at that point, it would have the same gradient as this line here, which is what this is saying here. Okay. So let's continue. So that's the mean value theorem. Since capital F is differentiable, so we know that from earlier. And if it's differentiable, it's continuous. We can use the mean value theorem. So it's differentiable and continuous on each little subinterval. So xi minus 1 to xi. Mean value theorem says that there is some ci in between that interval. Xi minus 1 to xi such that capital F dash of ci equals f of xi minus f of xi minus 1, oh, apologize for that, xi minus 1 on xi minus x. Very good. So we have this equation here, and let's just play around with it a little bit. So this is from earlier, just f of ci, little f of ci, that equals f of xi minus f of xi minus 1 all over. So instead of writing this out, the way we've defined it before is it's just the change in xi. And from that we get f of xi minus f of xi minus 1 is just so f of ci, and then we're multiplying both sides by the change in xi times the change in xi. Okay. And with this equation, we're going to take sums from I equals 1 to n of both sides. So let's consider the left-hand side of this new equation now. So what happens if we're taking sums of these things? So let's kind of, let's expand it. So let's start from I equals 1. We have f of x1 minus f of x0. So that's I equals 1. You're adding I equals 2 now. F of x2 minus f of x1. You can see the pattern. Plus f of x3 minus f of x2. And you continue this until you get to f of, well, we finish at n, so f of xn minus the previous term, xn minus 1. Okay, so notice we can get some cancellations. This will cancel with this will cancel with this, and so on. And what you're left with is, by the end of, when you do all these sums, you're left with this and this. So these two terms. So that is just f of xn minus f of x0. And remember from earlier how we've set up our partition. x0 was just A, xn was just B. Okay. So this appears in the fundamental theorem. So it's a sign that we're almost there. what we're left to do is figure out what to do with this right-hand side now. Because we want an integral to appear. Actually, I should knock this out. So what we're doing is, if we're looking at the right-hand side, to make an integral out of this, you take Riemann sums, you shrink the change in x, and then you get the integral. So shrinking change in xi, you get that. Well, the limit as, so if we're shrinking xi, what we're doing is we're taking n to go to infinity, because n was the number of intervals we're making, so the number of points. And if we're taking n to be very large, what we effectively do is shrink the width of those subintervals to 0. So the limit as n approaches infinity of that right-hand side, which was the sum of I equals 1 to n of f of ci times change in xi, so that's just this. That's the definition of the integral from a to b, f of x dx. And that was equal to the left-hand side, which was this. So that's the fundamental theorem of calculus, proved in 2 separate parts.